So today I'm going to talk about context-aware robotics for human-centered environments. And I think I'll argue that as robots move into complex human spaces such as campuses and hospitals, uh, they require social and semantic intelligence, not just navigational capabilities. So let's see. Consider some everyday tasks. Okay. So imagine trying to find tortilla chips in your favorite tortilla chips in a grocery store, or trying to find a seat in a public space. These problems require understanding of the social cues and semantic cues. And imagine how difficult these tasks might be if you don't have the ability to see. So for people with visual impairment, this context is often inaccessible. And this makes the domain of assistive robotics a very rigorous test bed for context-aware robotic systems. So the idea here is that if we can build systems that can perceive and interpret environmental contexts good enough to guide a human, then we prove that the system truly understands the environment. Okay. Another motivation behind my work is rooted in addressing the limitations of the current existing assistive robotic systems. So current systems are geometrically competent. They don't hit walls, but they lack the understanding of human context. They can guide you down a hall, but they cannot tell which seat is appropriate for you to sit in, or which shelf holds your favorite pasta. And some systems have tackled complex environments such as grocery stores. For example, the seminal work by Gharpure et al. But they often rely on augmenting the environments through RFID tags or other beacons, like this work as well. And furthermore, providing fine-grained grasp guidance is underexplored. Existing methods such as the ones using a quadcopter, a manipulator arm, or mechanical turk are often impractical or complex or rely on human availability. So to bridge this gap, we need systems that interpret the environmental human context. We also want it to be less expensive and be infrastructure free. And we also want it to be practical and low profile and low cost. So this brings me to my thesis statement, which is context-aware embodied AI systems that use social, semantic, and spatial environmental cues can produce more useful guidance and more reliable spatial groundings in human-centered environments. Okay, so here's an overview of the research work I'm going to talk about today. I won't spell out each thing right now, and if these words don't mean anything to you, don't worry about that. I'll explain them soon. And okay, so brace yourself for a lot of research work. So I mean, I already bribed you. So, okay. So the first work explores using social cues for goal-based navigation, enabling vision-independent participation in the choice in the social dynamics of seat choice. And this work was presented at IROS 22. Here in this table, you can see that Wang et al. Showed that finding empty seats in public crowded places is one of the most important mobility tasks, and a task where a white cane doesn't have a lot of utility. And it turns out this problem is fairly difficult and nuanced to solve. For example, here, this is a photo taken in the CU Boulder lobby, and these are not planted actors. This is one random day. So it is not enough for us to just identify a seat's location. We also have to be able to identify whether it is appropriate for us to sit in a place. And prior work also showed that people prefer to seat themselves in a way that optimizes for their privacy and intimacy. So yeah, for example, if you see this photo, you can see that people like to take seats closer to the walls. And we'd like to refer to these seats as anchored. And this increases the sense of privacy. And we also see that these students optimized for reduced intimacy as they chose seats away from strangers. And common aids like canes cannot find seats in any targeted capacity. And guide dogs are very costly and thus not scalable. And apps like Be My Eyes depend on again, the availability of humans. So our solution uses a perceptive robotic cane equipped with color and depth cameras for sensing and vibration motors for haptic feedback. And we use a backpack-worn laptop for processing. So let's see how the system works. At the beginning, the system starts with like SLAM, off-the-shelf SLAM and object detection, and it does and identify all the goals, and that is followed by goal scoring. So once the goal is scored based on social preferences, we plan towards the goal. And afterwards, the plan is conveyed using auditory and vibrotactile feedback. And the auditory feedback is used to provide the plan overview, and the vibrotactile feedback is used to provide online navigational guidance. So let's start with a demo. I like to start everything with a demo, and then we'll discuss the details of how this works. So in this video, you can see a scenario with 2 chairs in the room, along with a bunch of obstacles. And these are novice users who have never used a cane to navigate. But as you can see, this novice user is not able to locate a chair without guidance. But with our system, the user is not only able to locate the chair, the system is also taking them to the chair with higher privacy. And in the next run, the system notices another human. And this time, it leads the user to the chair, another chair, to lower the intimacy with stranger. So the smart cane did not just avoid obstacles here, it optimized for privacy and intimacy. Okay, so now let's get an intuition on how the goal scoring incorporates these social preferences. So we are interested in assigning higher scores to seats that are more private. And our key insight is to overcount contiguous obstacles. And because they are similar enough to walls. So our anchor scoring algorithms introduces a sliding window, and it increases the anchor score if majority of the rays within this window are in collision. And smaller objects do not count for privacy, and the window slides past them without increasing the score. We also formulated a proximity scoring metric to account for other social properties. And we increase the proximity score if the goal is closer to the user to account for convenience. We also increase the score if the goal is closer to objects of similar class, because that increases the likelihood of you finding one of the desired classes. We decrease the score if there are nearby objects that are associated with a higher chance of the seat being taken. For example, a backpack or a mug near a chair. And finally, we decrease the score if there are humans close to the goal to lower the intimacy with strangers. We conducted a pilot study with 6 blindfolded people in 3 different room layouts designed to test the baseline performance and the system's ability to select goals based on proximity and anchoring. So our pilot was successful in validating the system with novice users, and we saw a 100% success rate at finding any seat. And we achieved an 83.3% success rate at finding the socially preferred seat. And the users were also, most of the times completely able to avoid the collision. Because I've seen from this chart that the average number of collisions per trial is less than even 1. The users also reported positive user experience. They provided high ratings for measures indicating things like confidence in navigation, ability to find the goal, and verbal overviews helpfulness. So in conclusion, our system could successfully assist in finding and guiding users to socially preferred goals. Okay, so next, I'll focus on learning decision-making policies from human actions and behaviors. And I found, again, the providing grasping guidance to people with visual impairment as a compelling and challenging use case for this problem. Our system described in the following slides is called Shelf Help. and we presented it at AMAS 23. This shelf help exploits the semantics of the scene for target retrieval and then employs a guidance system learned from other cited guides. And in this case, by semantics, I mean grocery products and their types. Okay, let me again remind you of the challenges of grocery shopping. So grocery shopping is hard for people with visual impairments. They usually work with cited guides, and that causes a lack of independence, and in turn also causes a loss of privacy. And finding, this is from our local King Supers. Also, the finding a product is a complicated visual challenge. For example, in the US market alone, they introduce around 30,000 new products each year. So a modern computer vision object classifier simply cannot keep up. Moreover, similar items are packed together, so making it very hard to differentiate them based on just tactile feel. So our solution was to use the same robotic cane, but we extended the abilities this time. And in this case, the guidance is provided verbally via the laptop speaker instead of vibrational motors. Okay, before we proceed, I want to briefly mention the core contributions of this work, which are a modular two-stage computer vision pipeline to detect the desired product on the scene, and then a novel fine-grained grasp guidance system that optimizes for guide time and command count. Okay, once again, I'll start with a demo. But before I play the demo, note the upper right corner. So in this case, the computer vision has done its thing. It has identified the desired product and highlighted it with a red bounding box. And on the bottom right corner, you can see the live camera view as the user approaches and selects the product using the verbal guidance. And here's the demo.
I found the product at about 11 o'clock direction. Move 6 inches up. Move about a foot to the left. Move far forward. Move to the left. Move forward. Go ahead and grab the item.
Okay, now let us see how the system works. So this as the very first step, the system starts by issuing commands to assist the user to align to the shelves plane, so that the system can give commands with respect to the shelves plane. It then detects products and performs data association. This is done because we see like products at 30 FPS, so we need to maintain a persistent memory. Once a target is selected, the system creates a guidance plan using a Markov decision process based planner, and we'll talk more about that. And finally, the system provides verbal guidance, which starts with a plan overview, which informs the user about the general direction of the product, and it's followed by movement instructions such as move 6 inches to the left. Okay, now let's see how the product detection pipeline works. So so the product detection requires a target image of the target product in hand. And the algorithm has two major steps. In the first step, it proposes regions most likely to contain any product, not the desired product, but any product. And in stage 2, we extract the visual features of the desired product and for all the proposed regions using an autoencoder. Once we have the features for the target products and for all the proposed regions, we compare the features using cosine similarity to find the best match on the scene. And then guidance is planned using the Markov decision process. And here we mapped, as the first step, we collected human demonstration data where we mapped human verbal instructions to actual hand movements. So here you can see in the plot a sample of some of the commands and some of the actual end effector movement or hand movement that the commands caused. So that was the first step. And then we fit a Gaussian on this hand movement data that gives us a mean and a standard deviation for each verbal command. So now let's formulate this MDP. So the set of verbal instructions make the action space in this case. And the Gaussians help us form the transition probabilities. And the relative hand position forms the state space in this case, relative hand position to the goal. And we designed the reward function to encourage reaching the target efficiently and discourage issuing superfluous commands by penalizing unnecessary axis changes. Because you can imagine if the system asks you to go left and then up, then go left, then up, it could get quite irritating. So finally, we solve this MDP offline. And we query the generated policy online to obtain the best action for any state. That is the best verbal command for any state. So, and then we conducted an IRB approved within subject study with 15 blindfolded novice users. And this study compared three conditions. It compared our discrete planner, shelf help, which would say things like move 6 inches to the left, with a continuous planner, which was just a visual servoing baseline. So it would say things like keep on going left, and then it will ask you to stop. And then we also compared them with a human guide, which we consider to be the gold standard of guidance. And in this case, they were allowed to use video call and free-form speech. And now let us see some results. Here on the left, you see left plot shows the average number of commands issued by the planners. And on the right, you see the average guide time spent by the planners. And shelf help in orange outperformed the baseline continuous planner in blue, both in terms of number of commands and guide time. And we also observed that shelf help matched human level assistance for the same metrics. Shelf help also elicited positive response for perceived intelligence, competence, and confidence, but it was rated slightly lower for interactive and human-like metrics. And in exit interviews, we found out that people wanted more grounding and things like, so far so good, doing good so far, and things like that. So to conclude this project, we saw that independent grocery shopping is a challenging visual task for people who are visually impaired. And shelf help provides a solution to the product retrieval subtask. It can locate items and verbally provide manipulation guidance, enabling people to independently locate and retrieve items from shelves. And the user study revealed that shelf help objectively matches human level assistance, but falls short on human-like interactive metrics. This work was also featured in some media. And so moving on, we realized that to truly provide context-aware guidance, the robot or the AI system needs to know exactly where it is. And a problem that was largely unsolved in many day-to-day environments. So which brings me to my work on semantic localization in quasi-static environments like grocery stores. So shelf-aware is a semantic particle filtered localization system that uses low-cost and low-profile hardware. For example, grocery stores are quasi-static because if you map all the products in a store and then come in a week later, everything would have moved. The products wouldn't be there. So, and this is very challenging for algorithms that rely strictly on visual features. And again, just to recall, localization is how a robot determines its pose, which is composed of its position and orientation within an existing map. And I would argue that this is a prerequisite for all autonomous navigation. So here, let me again remind you of the issues in this kind of environment. So here you can see a top-down map of our mock store that we constructed in the lab. So here, the uniform nature of aisles makes the depth data ambiguous, even in this small representation of the store. And constantly changing stock further complicates things. And of course, we are not the first one to tackle this problem. To create a navigation system for grocery stores, or neither we are the first system to use semantics in Monte Carlo localization framework, but prior work either uses RFID tags or require floor plan or uses expensive and bulky hardware like LiDAR or wheel odometry, or they require the landmarks to be fixed in count. Our approach aims to overcome all of these limitations. So the key insight is that instead of treating products as static landmarks, we model them as probabilistic distributions over object counts and their spatial arrangement. So our semantic vector essentially captures what is present in the scene and in which direction and how much. This allows us to handle the quasi-static nature of the store where stock changes perpetually. So shelf-aware requires only an RGBD camera and a visual odometry camera, and without needing any expensive LiDAR or pre-installed beacons. And as you can see in the image, it can be mounted on existing carts or robots or be worn as a wearable. And let me tell you why this is important, because without wheel odometry, you cannot really tell how much the robot has moved, how much the wheels of a robot has turned. And we have to solely rely on visual features. And without LiDAR, we don't get accurate distance information. So in a sense, we are very excited for that shelf-aware works the way it does. Okay, now let's dive into how the system works. In the first step, we create a semantic map. And for that, we trained a ResNet 50-based classifier to classify products into a fixed number of classes. And then the semantic map is a discretized 3D map that is built by aggregating product class information to form discrete distributions of counts for each of these 3D grids. So each of these 3D grids would contain many products. Okay, so let me give you an intuition on how the semantic localization framework works. So we need to build the map once, and then we can perform repeated localization on that map. So here, the system has arrived on the scene. It calculates, it looks at the scene, and then calculates the semantic observation vector from the RGB image and a 2D depth reading analogous to a line LiDAR reading from the depth image. So we now have two observations. And this image here illustrates a 2D top-down view of a mock store. And this store has two aisles, and particles in a particle filter system each try to guess the robot's location. So in this illustration, there are three particles, and they are holding three different pose hypotheses. And based on the observational evidence, I will decide which particle is the closest to the reality. So as the first step, we calculate expected depth observations for each of these particles by raycasting. And then the expected depth observations are compared with the real depth observations. And better matches lead to an increase in weight for the corresponding particles. Okay, clear so far? Okay. Likewise, we also calculate the expected semantic observation for all the particles by raycasting on the semantic map this time. And we then take the real observed semantic vector that you can see on the top right, on the top middle, and obtained by parsing the image. And in the previous step, we had already computed the expected semantic observation for each of the particles. Okay, so now we compare each particle's expected observation with the real real semantic observation. And in this illustration, the topmost particle's expected observation has the closest match. And then this leads to the higher semantic weight for that particle. So after combining both the depth-based weights and the semantic weights, the worst performing particles fade away due to lower weights. Okay, let's again dive into a demo, which was done in the mock lab. So here, in the demo of the system, you can see the top-down view of our store. And you can see the ground truth trajectory is in purple, and the end of the red arrow shows the predicted pose here. And our system starts with the correct global localization, and it then loses it because there's no semantics where it's looking at. And then once it encounters semantics, it converges back. This just shows how challenging the task is without wheel odometry and LiDAR. Okay. So let me now talk about some results. We tested shelf-aware by varying conditions to include dynamic obstacles and degraded semantics. And all in all, in the controlled lab environment where we had the mocap system to have the ground truth, the system achieved 97% global localization success rate. By that, I mean the ability for the system to guess its location for the first time. And tracking is the ability to do so in a continuous way after the first global localization. Uh, it beats the geometric baselines like Monte Carlo localization and the ROS, the standard AMCL. We also have a baseline that represents a semantic Monte Carlo localization framework where the semantics are fixed in quantity. And yeah, here are some samples of ground truth trajectories in blue and shelf-aware's predicted trajectory in red. We also evaluated the system in an operational 3,500 square feet store. Uh, and uh, and here you can focus on G% is just the global localization success percent. So we have a drop compared to the mock store, but we still beat the next best baseline by more than 50%. And we performed an evaluation where we provided the system with ground truth semantics. And in that case, our system was able to extract the most information and got very close to full success. But another systems were not able to extract information even from the ground truth semantics. Okay, next, I'll talk about our work where we used richer and more discriminative features to improve global localization in diverse environments. So we go beyond grocery stores in this time. This work is called VLM Clock. Clock stands for global localization. And this is VLM enhanced Monte Carlo localization in aliased spaces. And this work is currently in submission. Okay. Hopefully, I've already convinced you why global localization is hard, but I'll do that again. So, uh, consider these environments like offices and grocery stores. They have repetitive geometry. They have repetitive geometry. They even have repetitive semantics, like the same chair, same monitors, and places like grocery stores have long tail semantics, and we know that makes things very complicated for computer vision algorithms. So, knowing that there's a chair or spice doesn't help us disambiguate. And prior work has so far used simpler top-level fixed classes. But VLM Glock uses rich discriminative semantics. For example, our system wouldn't just say a chair, it would say a black mesh chair with orange cushion. So we hypothesize that VLMs help in three ways for localization. So they produce discriminative language. For example, this cabinet from the lab, it's just a cabinet, but a VLM described it as yellow just right flammables cabinet. We also hypothesize that VLMs can do implicit quality filtering and can remove unreliable features or objects, for example, blurry objects or unreadable things or observations that have low confidence. We also hypothesize that they can reason about objects that should matter for localization and reason about their permanence. So here in this image, the system has tagged a chair as a quasi-static object because you come to the scene the next time and the chair might not be there, but it would still be the same scene. So again, let's see how this method works. So as the first step, we create an offline semantic map where the VLMs generate the rich descriptions. Then these descriptions are passed through a fine-tuned mini-LM text encoder. And then they are recasted and projected on the map, on the 2D occupancy map. So here you can see the two domains that we operated in. The left side is an office space. It's our office. It's the Intelligent Robotics Lab. That's a 3,700 square feet space. And on the right side, you see the 3,500 square feet grocery store. And I sprinkled some semantics on that. So, okay. Don't worry about this thing. We'll dive into this slowly. So this is the whole localization pipeline, which essentially fuses the rich semantics with a traditional particle filter. So, like I told earlier, we tested VLM Glock on two domains, a lab domain with a unitary Govan quadruped with a LiDAR, and another was a grocery store with a consumer cell phone. So as the first step, VLM block takes RGB images, range readings, and odometry. And as the first step of the operations, it produces the rich language descriptions and then language embeddings. We then employ an inverse semantic proposal to compare the scene embedding with every semantic map cell. And then we retrieve the top pose modes. And then particles are seeded around these semantics. So instead of relying on purely uniform search, we seed our semantics through this, which you can see this illustration. This is actually not an illustration, this is real data. So then thereafter, once the semantics have dominated, which is important because we don't want the geometric observation to collapse the probability prematurely. Because in repetitive areas, you can have places that have similar likelihood. So after that, the range information helps us refine the pose. And yeah. And after that observation has been accounted for, VLM Glock then selects the most dominant mode and then reports the mean pose. So let's see if the results satisfy our hypothesis. So the first hypothesis was that VLMs can give you rich text features that are discriminative for localization. So in this case, you see. So we compare it with AMCL, which is geometric baseline, and a fixed class semantic Monte Carlo localization. So it's inspired by our previous algorithms, where we just keep the top class level information and not the rich descriptions. And VLM Glock beats them comprehensively in both lab and grocery environment. Okay, the evaluations also support the other two hypotheses. So here we kept the blurry images. So because the VLM labeled blurry images for us, so if we include the blurry images, the global localization success rate drops by 29%. So accounting for all visual features of the scene is not a good idea. And VLMs can help you disregard bad features. And VLMs can also do permanence reasoning. So in this experiment, we removed all the tags. We removed all the tags like such as static, quasi-static, or dynamic. We removed the tags and used and did the localization, and that also dropped the performance by 8%. There's one more information. There's more you can do with the permanence information though. So here in the scene, you see the scene. You see a quasi-static chair, and you see the whole description of the scene. So what we use this quasi-static data to do data augmentation, and we dropped out quasi-static things because they should not affect the scene. They could be present on the scene or not, and so we did that. So we actually did not remove the chair. We just removed the chair from the scene's description, and so we saw that if we skip this the fine tuning of the text encoder obtained through this data augmentation, that also drops the performance by 19%. So the results show that VLMs not only help through open vocabulary object names, but through rich descriptions and reliability cues and reasoning about the scene permanence. So, okay, here's another demo for you. This is a GIF on a loop. So where you can see the ground truth pose is in red, the predicted pose is in green, and the particle cloud is in blue. You can see that VLM Glock enables, and this is in the real grocery store. You can see that VLM Glock enables quick convergence and gets really close to the ground truth. Again, the takeaways here are that VLM Glock improves localization across two very different real-world environments. It shows that VLMs can be used to generate rich descriptive features, and that they can also do quality filtering and do permanence reasoning, and these things are important for localization. And the bigger takeaway is that by treating language as evidence and combining it in a particle filter, we gain the robustness of foundational models while keeping the geometric precision of the filter. Okay, so this brings me to my last work that I want to present. This work is in preparation right now. Here, we move on from localization to a broader question. So we saw that once we have extracted these rich descriptions from the scene, how should a robot use them in order to do many more things and achieve many more tasks? So this final project is called GEST, multimodal knowledge extraction and spatial grounding. Uh, and one of the core questions that we asked in this is specifically what in a spatial representation makes VLM-generated guidance groundable? And our analysis has surfaced that an anchored semantic topology as a minimal enabling component. And we'll talk more about what I mean by an anchored semantic topology. So let me provide you with an overview of all the popular spatial representations and what they offer. So some of you might be familiar with metric maps. So think about 2D occupancy maps. They are great at providing you information about traversability and distances, but they do lack semantic awareness. And then there are VLMs. Like they're just their internal representation. They are semantically rich, but they are weakly spatially grounded, as shown by one of the recent works, a recent VLM navigation benchmark called Navitrace, and there are many more work that shows that. And then scene graphs. Scene graphs are really popular. They give structured object relations, which are good for planning, but they are not always good for generating legible route instructions. So just instead like binds VLM generated semantics with a lightweight topology. Okay, again, let's see an overview of our approach. The key point is that we are just going to use one mobile scan to create a reusable spatial knowledge layer. And this layer is not task specific. This layer, the same representation supports multiple downstream tasks, as we'll see. So again, as the first step, the system takes an RGB image, a depth image, and uses off-the-shelf SLAM poses as input. And then, as the first step, we select keyframes that are sufficiently different, and we select representative objects, and then these objects are annotated using a VLM. We then project these rich semantics on the 2D occupancy map. Again, created using off-the-shelf SLAM algorithms, and then extract a skeletonized walking topology graph. This is the graph for the grocery store. Right? And finally, we show our system's ability to system's rich description to support various downstream tasks, such as global localization, zone classification, semantic search, and navigation instruction generation. I won't talk about the global localization part because we developed that into a fully mature project, which I just talked to you about. For the other tasks, we tested GIST's performance in the same grocery store from before, as the environment still presents a compelling example for geometrically repetitive and semantically dense environment, and it was a really cluttered space. So that was a challenging space to work with. So here we used Voronoi-like classification for each pixel to do a pixel-wise category estimation, and this was done autonomously from the VLM labels. For example, there are patterns that we observed from this. So if you observe the upper left corner of the store, you can see that there are multiple categories present there. And upon investigation, we saw that all of those categories were organic. So that store likes to keep all of their organic things in one aisle. And we saw all these emergent patterns automatically discovered from our representation. We also see that the rich semantic descriptions can enable intent-aware search. For example, we created a search system where now I search for vegan protein here, and vegan protein is not a product per se. And the system was able to find the products that are the most likely satisfy the user query. And it also gives the justification for that. You can see it would say things like high protein chickpea, high, pro, popular vegan meat alternative, and things like that. And the system knows that the exact item is missing, so it also suggests a fallback and a semantic zone most likely to contain the user query. So you can say navigate to the estimated location of lentils, beans, and pulses. We also tested the system's ability to generate natural language navigational instructions and compared them against Nav Composer, which is a visual sequence-based baseline. So it takes a sequence of images, and with Naive Gemini, which takes all our prompt, but it doesn't have any topology information or any semantic landmark information. So in this case, we we provide our information in two ways. We provide our information also through images, but we also provide the topology and semantic information just through text. So it's the same information through text. And you can see our algorithm beats Nav Composer and Naive Gemini across 15 different routes. And on metrics like egocentric clarity, landmark utility, low cognitive load, safety and completeness, and view independence guidance. So view independent guidance are instructions where you don't refer to things that are present in the view. So they are egocentric. So you don't say things like go here and go there and things like that. And here we show, and we use LLM as a judge method with two held out LLMs to score these. And we only show significance here when both the judges independently agree and have significant results. And we show the lower of the p-values here. You can see here that our visual system is only marginally over our text-based system. And it's not statistical different. So we wanted to investigate that more, and we did further evaluation studies to figure out what makes a VLM routing groundable. So here in this plot on the left side, you see the things that we have removed from the prompt, the information that we have removed from the prompt. And on the right side, on the x-axis showed the drop in the total number that you saw earlier. So we saw the most important drop was when we removed the route text and the landmark text, which were both computed by the topology and the occupancy information. So this suggests that the core benefits come from the structured route and landmark representation, while the visual map serves mainly as I would say, a compact interpretable visualization. And it does add slight additional grounding. So the key takeaways are VLMs provide rich semantics, but they are not great at spatial grounding. Semantic topology binds VLM labels to a lightweight topology. And the route quality mainly comes from the computed topology structure and validated landmarks, and not from strict visual representations. And that this representation supports search, localization, zone inference, and route language. So yeah, I guess with this, I'm nearing the end. These are the papers and journals referenced for today's presentation. And yeah, just to provide a small summary, my work, I showed work related to designing for social context, learning policies from human action, and localization in quasi-static environment, and multimodal knowledge, spatial knowledge and extraction and spatial grounding, and VLM enhanced semantic localization and mapping. And in summary, I would say my work establishes foundational techniques for interpreting and modeling environmental context to create systems that can operate in human-centered, cluttered real-world environments. And I guess that is my last slide. And with that, I would like to thank all of you on Zoom and in person that come here for attending. And first and foremost, I would like to thank Brad for all of his guidance and for giving me a chance and helping me discover what I want in life and that I want to pursue this line. And the whole committee, my lovely wife, my friends, my family, everyone. And yeah, that's all from me.
All right, do we have any questions from the audience?
Jay, I have a question. Great pop. I was wondering if you could comment broadly on what you see the role of VLMs in sort of the social context, social navigation side of things. You know, you made a good case that it was important to incorporate, like social norms, but enumerating them and explicating them, that seems challenging. Whereas a VLM might intuitively know some of these things. Have you thought about that at all?
Yes, yes.
Can you repeat the question?
Oh.
Just clearly?
Yeah, I think the question was regarding the like how VLMs would shape research with social norms, because they can handle more social norms and that the social norms wouldn't have to be hand coded. And I agree with that sentiment. And I think this is exciting. For example, remember in one of the works, we mentioned that the system was efficient but not interactive. So VLMs can easily aid with that. And though some work has shown that VLMs do ignore certain cultures and are more trained on cultures, so they do have biases even for social norms. But I think I think it should be incorporated, and this would be lovely for social navigation. Yeah.
Curious about an ELM block. How does it know which objects to derive textual?
Oh, yeah, that's a good question. So the question was about how does VLM Glock know which object to describe? Gemini. So we use Gemini as our the powering VLM layer, and Gemini does have an object classifier as well, so it can create bounding boxes. So the first step of the system is to create bounding boxes of the desired things that you want the system to describe. And I found that Gemini was better at identifying stranger things like non-obvious classes. So in this project, we use Gemini as the first step.
The follow-up.
Yeah.
Is it that I know, like in an office, describing the computer screen is not very useful. Do you see that? Where do you try to prompt it? Otherwise, we might have a lot of textual descriptions that are just
Yes.
very useful.
Yeah. So in a repetitive environments, there are repetitive semantics, but there are still areas. Okay, so this question was about ignoring repetitive semantics, or whether we should incorporate them or ignore them, because are they adding value? And I would argue that they do add some value, because there are, like for example, in the office spaces, not all the viewpoints will make you like see a monitor. So it still narrows down the search space. And also, we used a fine-tuned language encoder. So the idea here is that the language encoder learns to ignore certain text, because we are using a language encoder to encode what the VLM has described, so that the encoder should transform these into features which are more important for localization. So that layer also carries the weight to, yeah, okay, pun intended, carries the weight to ignore some of the semantics.
Sorry, it's a little more, but this is a little in the weeds. I'm surprised. So you use the VLM to filter out blurry images.
Yeah.
Is there no algorithmic way to detect a blurry image that seems?
Yeah, there are classical computer vision ways which look at sharp lines, and like any other, like previous gen image processing ways, they are very brittle. And so even if you have blurry lines, pixelated things, they still have lines. So they do have a lot of false positive and false negatives. So they were not great for my use cases in real world, but they do exist.
All right, let's thank Shavendra again. At this point, I'll ask everybody but the committee to leave.
we are waiting for everyone to leave, and I would request the Zoom people to also leave, apart from the committee.
You made.
Yeah.
You can stop the recording if that works.
Oh, yeah, maybe. Um,